Hello there, and welcome to the Sleepy Explainer. Imagine, just for a moment, that black holes aren't cosmic monsters devouring everything in their path, but something stranger, doorways. Not just to other places, but to other times. It sounds like pure science fiction, but when Albert Einstein reshaped our understanding of the universe in 1915, he accidentally left us with a puzzle that still haunts physicists. If space-time itself can bend, twist, and stretch, then maybe, just maybe, it can also fold back on itself. Time travel isn't some wild fantasy. In fact, it already exists in subtle ways. Astronauts on the International Space Station age a tiny bit slower than people on Earth thanks to the relativistic effects Einstein predicted. That difference is small, fractions of a second, but around a black hole, the effect magnifies into something jaw-dropping. Suddenly, science fiction begins to blur into science. So tonight, let's explore this frontier step by step. From the mathematics of Einstein to the wild horizons of black holes, from paradoxes that twist logic to visions of civilizations using gravity itself as a time machine. This isn't just a bedtime story, it's a journey into the deepest question of all. Can black holes really let us cheat time? If time feels like an unstoppable river, black holes are the places where the river doesn't just bend, it fractures. Einstein's equations predicted that the closer you get to a massive body, the slower time ticks. It's called gravitational time dilation. On Earth, the effect is tiny. A person living at sea level technically ages just a hair slower than someone standing on a mountaintop. But scale that up. Imagine a spacecraft hovering close to the edge of a black hole's event horizon, while its twin ship drifts safely farther away. To the distant observers, minutes might pass. For the crew near the black hole, hours, days, maybe years. This isn't science fiction, it's tested. In 2010, physicists used ultra-precise atomic clocks on airplanes and satellites to prove the effect beyond doubt. The universe keeps two clocks, one for the far and free, another for the near and bound. So when we talk about black holes as time machines, we don't mean a DeLorean or a glowing portal. We mean a real physical manipulation of how the universe itself counts the seconds. And the closer you dare to that event horizon, the more extreme and tempting the possibilities become. But here's the unsettling part. What happens if you go too close? What happens if you drift too close to a black hole's boundary, the infamous event horizon? Imagine standing on a cliff where every step forward doesn't just lead down, but out of time itself. From the outside, anyone watching you fall would never actually see you cross the horizon. Instead, your image would freeze, stretched and dimmed, as if the universe itself couldn't decide whether you were still there. Seconds for you become centuries for them. In effect, you would become a ghost on the edge of eternity, forever locked in slow motion. But from your perspective, you wouldn't feel the freeze at all. You would keep falling faster and faster until nothing, not even light, could carry word of your fate back to the universe. Physicists call this the point of no return, and it's where time, space, and causality stop behaving in any way our minds can truly grasp. And here's where the idea of time travel begins to blur into reality. Because near the horizon, relativity doesn't just slow clocks, it reshapes futures and pasts, carving out strange corridors in space-time. But what if you didn't fall in? What if you found a way to ride the edge, hovering in orbit, surfing on the boundary of forever? Could you live in hours while the universe outside aged by millennia? Imagine your ship equipped with engines strong enough to resist the pull of a black hole, allowing you to hover just outside its grasp. You wouldn't fall in, but you wouldn't escape either. You'd be riding a razor's edge, a cosmic tightrope where physics begins to play its strangest tricks. Here, time slows so dramatically that the outside universe races ahead. A few hours of orbit for you could equal hundreds, even thousands of years for civilizations beyond. It's not science fiction, it's pure Einstein. His theory of general relativity predicts that gravity bends not just space, but time itself. The stronger the gravity, the slower the clock. This effect isn't just theoretical. We've already measured it with satellites orbiting Earth. Astronauts on the International Space Station actually age microseconds slower than people on the ground. Tiny differences, yes, but magnify that effect by billions, and a black hole becomes the ultimate time machine. And this opens up a staggering thought. While you orbit in this distorted bubble, entire epochs could unfold outside. Empires might rise and crumble. Stars could flare and die. You would return after a short journey, only to find the galaxy utterly transformed. But here's the real hook. Black holes don't just slow time. In their depth, some theories suggest they might redirect it. Could falling into one be more than an end? Could it be a passage? If black holes can stretch time, what happens if they bend space so violently that it folds back on itself? Mathematically, Einstein's equations don't just allow for this. They demand the possibility. The result is something physicists call an Einstein-Rosen bridge, but you've heard the name whispered in science fiction. A wormhole. Picture it. Instead of falling into a crushing singularity, the tunnel curves through space-time itself, linking two distant regions. One side could lie light years away in our own galaxy, or perhaps in another galaxy altogether. Some speculate it might even link to another universe. The catch? No one knows if these bridges can remain stable. Gravity tries to slam them shut faster than light can travel through. And yet theory offers loopholes. Exotic forms of matter with negative energy could hold a wormhole open long enough for a traveller to pass. Physicists like Kip Thorne, who inspired Interstellar, have shown that the math works out. That doesn't mean wormholes exist, but the equations leave the door tantalizingly ajar. So imagine standing at the mouth of such a cosmic tunnel, with a star field shimmering on the other side. Step through, and you wouldn't just cheat distance, you'd cheat time. A journey that should take millennia could collapse into a heartbeat. But here lies the deeper question. If wormholes are real, who or what could have built them? Are they natural accidents of physics, or signatures of intelligence written into the fabric of the cosmos? Step through that shimmering wormhole and suddenly you're not just skipping across space, but you're colliding head-on with time itself. Physicists call them closed time-like curves, loops in space-time where cause and effect circle back on each other. In plain terms, wormholes could create pathways not just to distant stars, but to the past. But here's the paradox. Imagine traveling back to yesterday. If you step into the past, do you risk rewriting the future? The most famous thought experiment asks, what if you went back and prevented your own grandfather from meeting your grandmother? If that happens, how could you exist to travel back in the first place? This is called the grandfather paradox, and it's more than a science fiction gimmick. It's a real problem in Einstein's equations. And yet, some physicists argue paradoxes might resolve themselves. This is the idea of the Novikov self-consistency principle, that events in time loops adjust so contradictions can never occur. You might attempt to stop your grandparents from meeting, but something would intervene, maybe a coincidence, maybe sheer inevitability, to ensure history stays intact. Others propose an even stranger solution, that every paradox simply splits reality. Each action creates a branching timeline, spawning parallel universes where both outcomes exist. In one, you succeed in changing history. In another, history remains untouched. So, if wormholes are real, they don't just open doors to faraway galaxies. They may fling us into a multiverse where time travel is less about breaking physics and more about expanding it. And here's where the story deepens. If time can branch, Could black holes themselves be the seeds of these alternate timelines? If black holes really stretch space-time into extremes, then maybe they're not just destructive monsters swallowing light. Maybe they're cosmic engines, punching holes into other realities. Some physicists, like Lee Smolin, even suggest black holes could be cradles of new universes, each one budding off like a cosmic offspring, carrying its own laws of physics. Picture it. Inside every black hole could be an entirely separate cosmos, forever hidden from our view, sealed beyond the event horizon. From the outside, we see only a dark void, but from the inside, it might be the birth of another Big Bang. Now, let's tie this back to time travel. If wormholes can connect points in space-time, and if black holes might be natural gateways, then perhaps they're not endpoints at all, but bridges. What if a black hole in our universe links to a white hole, a theoretical object that spews matter and energy instead of swallowing it? In another, the passage between them could be the ultimate time corridor. This isn't just wild speculation. Einstein and Rosen first toyed with this idea in the 1930s, sketching what we now call Einstein-Rosen bridges. They found that in theory, space-time could fold so tightly that a tunnel formed, connecting distant regions. Later, theorists extended the idea. Maybe those bridges don't just span space, but time itself. Of course, the challenge is stability. Left on its own, a wormhole would collapse almost instantly. To keep it open, you'd need something exotic, negative energy, or matter that bends gravity in the opposite direction we normally see. Strange as it sounds, quantum physics hints such material might exist. Fleeting, but real. So, here's the haunting question. If black holes are indeed gateways, have civilizations far older than us already learned to use them? And if so, where or when might they be now? If black holes are natural gateways, then the next question almost writes itself. Could anyone out there already be using them? Think about it. We humans have only just begun to scratch the surface of relativity and quantum physics, but a civilization 1,000,000 or even 1,000,000,000 years older than us, they wouldn't just know the rules of space-time, they might engineer them. This is where the Kardashev scale becomes useful. It's a way of ranking civilizations by their energy use. We're not even a full Type 1 civilization yet, still fumbling with fossil fuels. But a Type 2 society, capable of harnessing the full power of its star, could conceivably gather the colossal energy needed to manipulate wormholes. A Type 3, spanning entire galaxies, might use black holes as transit systems, stitching together worlds across space and time. And here's the twist. Physicists already know black holes radiate energy, what Stephen Hawking called Hawking radiation. A super-advanced species might not fear black holes at all. They might farm them, stabilize them, and bend them into usable time tunnels. The haunting thought? If such beings exist, we wouldn't even notice. A civilization that can command space-time would move in ways utterly invisible to us. They could slip through epochs the way we step across a room. For them, history is not a chain, it's a landscape. But before we leap too far into speculation, let's ground ourselves. What would it actually take for humans to even attempt this? Could our species, fragile as we are, ever hope to ride the currents of a black hole without being torn apart? So, could we ever do it? Could fragile bone and flesh humans dare to ride the tides of a black hole? The first obstacle is terrifyingly simple. Gravity doesn't play fair. As you approach a black hole, the difference in gravitational pull between your head and your feet becomes so extreme that you'd be stretched like pasta. Scientists call this almost whimsically spaghettification. For us, that would be instant destruction. For a starship, it means materials and engineering beyond anything humanity can imagine today. Then there's the radiation. Black holes aren't silent. They blaze with accretion disks, swirling matter heated to millions of degrees, spitting out X-rays that would fry any unprotected ship. Even if you stayed clear of the accretion zone, you'd need shielding stronger than anything our technology has yet achieved. And yet, here's where the paradox deepens. General relativity doesn't forbid surviving such a journey. In fact, some solutions to Einstein's equations suggest that with the right trajectory, you might slip past the event horizon into a stable interior tunnel. The equations whisper, maybe, just maybe, there's a way through. It's the classic clash of physics, relativity versus quantum mechanics. One paints black holes as smooth, predictable curves in space-time. The other insists they're chaotic, foaming, unpredictable at their core. To build a time machine, we'd need not only stronger metals or faster rockets, we'd need a unification of physics itself. And that's what makes black holes so haunting. They are not just monsters of gravity. They are the gates to the next chapter of human understanding. But here's the twist that keeps even physicists awake at night. If black holes really are natural time machines, why haven't we seen time travelers yet? Why hasn't history been rewritten before our eyes? If black holes are truly gateways through time, then why aren't our skies crowded with tourists from the 31st century? Why hasn't some future historian appeared in ancient Rome, smartphone in hand, just to snap a picture of Julius Caesar? This is the puzzle scientists and philosophers call the time traveler's paradox. On paper, Einstein's equations don't slam the door on time travel, but reality seems stubbornly silent. There are a few possible answers, and each one bends the mind. The first is the chronology protection hypothesis, a phrase from Stephen Hawking. He suggested that the universe itself may enforce a kind of cosmic censorship, sabotaging any attempt to create closed time loops. According to this idea, the laws of physics simply won't allow paradoxes to exist. Try to build a time machine and nature finds a way to shut it down. The second is more chilling. Maybe black holes do allow time travel, but only forward. Step across the horizon and you might leap thousands of years into the future. The catch? There's no coming back. You're a one-way traveler into a history that doesn't remember you. And then there's the third possibility, whispered more in science fiction than science labs. They're already here. Maybe time travelers walk among us, blending in, careful not to disturb the timeline. After all, if you were from the future, wouldn't you be careful not to shatter history's fragile thread? The real haunting thought is this. When we look at black holes, maybe we are looking at the footprints of time travelers. A civilization older, bolder, stranger than our own could already have mastered what we only dare imagine. Perhaps the black holes dotting the cosmos aren't just collapsed stars, perhaps they're deliberate machines. And that idea leads us to the next, even stranger question. If black holes are machines, then who built them? Imagine this. You're standing on the edge of a cliff, staring into a vast, bottomless canyon. You can't see what's down there, but you know something is moving, pulling, dragging, reshaping everything around it. That's how black holes feel to us. They're not just strange astrophysical objects. They're enigmas that look engineered. Physicists have asked, could black holes be natural time machines? Or even worse, cosmic megastructures? Think of the scale. A black hole takes the mass of a collapsed star, or even millions of stars, and compresses it into a single point. Around it forms the accretion disk, matter spiraling in, heating up, blazing brighter than entire galaxies. For an advanced civilization, that's not a catastrophe, that's an opportunity. A black hole provides unlimited energy from its accretion disk, gravitational slingshot highways for interstellar travel, and maybe even time tunnels that link eras together. Some researchers, like physicist Nikolai Kardashev, imagined civilizations so advanced they wouldn't just harness stars, they'd tap into black holes. Why settle for a flickering sun when you could ride the engines of space-time itself? But here's the eerie part. When we look at certain black holes, they seem almost suspicious. Some are unusually stable, others strangely positioned. Could it be coincidence? Or could they be signposts, left behind not by nature but by intelligence? This is where the line between science and science fiction blurs. But remember, so did the idea of flying machines or quantum computers or even black holes themselves before we had proof. So let's ask the forbidden question. If black holes are engineered, who or what could possibly have built them? And more importantly, for what purpose? If black holes could be engineered, then we must ask, by whom? Not by civilizations like ours, clumsy and young, barely learning how to split atoms and launch rockets. Number. These would be the works of what astronomers call Type 2 or even Type 3 civilizations on the Kardashev scale. Let's break that down. A Type Y civilization controls the energy of an entire planet. Type 2 harnesses the power of a star. Think Dyson spheres, solar systems turned into batteries. Type 3, that's the real leap. They wield the power of an entire galaxy. For them, black holes are not monsters to be feared, but tools in the toolkit. And here's the twist. Some scientists argue that black holes might actually be the ultimate test of intelligence. Why? Because any advanced species seeking to survive billions of years would need something that lasts longer than stars, longer than galaxies. Stars burn out, planets crumble, but black holes, they can endure for trillions of years. Now imagine, what if a civilization, long vanished, seeded black holes across the cosmos as time vaults, places where knowledge, signals, or even entire worlds could be stored? Inside the event horizon, time behaves differently. A message, a probe, or even life itself could, in theory, be preserved for unimaginable epochs. Think about it. Maybe when we look at the night sky, we aren't just seeing natural accidents. Maybe we're seeing the fingerprints of survival strategies, messages written not in ink or light, but in the very fabric of gravity. And yet, there's a chilling possibility. If black holes are machines, if they were placed deliberately, then perhaps we were meant to find them. If black holes are more than natural accidents, if they are machines, then what could they be used for? The answer that keeps resurfacing, both in scientific journals and in science fiction, is almost unthinkable. Time travel. Picture this. You're a spacecraft, drifting ever closer to the event horizon of a spinning black hole. From the outside, an observer sees you freeze in place, as if caught in amber, your clock ticking slower and slower until it seems to stop. But inside your ship, time flows normally. Minutes pass for you, while centuries or even millennia pass for the universe beyond. This isn't imagination. It's the raw mathematics of Einstein's relativity. Gravity doesn't just bend space, it stretches time itself. And near a black hole, that stretching becomes so extreme that the future of the universe can rush by while you remain, in essence, anchored in the present. Now here's where it becomes more than a curiosity. What if advanced beings used this trick deliberately, not as tourists, but as strategists? Imagine a civilization facing extinction. Their sun is dying, their world becoming hostile. Instead of struggling against nature, they dive into a black hole's gravitational well, park their world on the edge of its horizon, and wait. From their perspective, it might feel like 1,000 years. From ours, billions. They step out into the cosmos when it's ready, long after other civilizations have burned out. And yet, this idea holds a paradox. Because if time travel is possible near black holes, then who is watching us right now? Could we be glimpses in someone else's carefully controlled timeline? Black holes, then, are not just cosmic mysteries. They may be doorways to different eras, different outcomes. If black holes can bend time, could they also bend space itself into something far stranger? Einstein's equations hint at an astonishing possibility: wormholes. Think of them as shortcuts through space-time, tunnels connecting two distant regions of the universe. A spinning black hole paired with its mathematical mirror called a white hole could, in theory, form one mouth of such a tunnel. Enter at one end, emerge at another, perhaps light years away. This isn't just theory for dreamers. In 1935, Einstein himself, with Nathan Rosen, sketched the idea of these bridges. Decades later, Kip Thorne and others asked the next question. If such tunnels exist, could they be stable enough to travel through? The math suggested yes, but only with a catch. They'd collapse in an instant, unless some exotic form of negative energy kept them propped open. Now, pause here. Doesn't this sound eerily similar to myths we've told for centuries? Portals, gateways, hidden doors between worlds. What if ancient stories of sudden journeys, vanishing for moments, returning decades later, were cultural echoes of something real? Not fantasy, but encounters with the strangest physics nature allows. And if wormholes can exist, then time travel isn't just about peeking into the future from the edge of a black hole. It could mean stepping sideways into a parallel now, or backwards into history itself. The story shifts here from survival strategy to cosmic adventure, black holes as transportation systems. For civilizations older than ours, these tunnels could be the highways of the universe. We may look up at the stars and see silence, while they look at black holes and see roads. If wormholes could exist, and if civilizations could master them, then here's the haunting question. Where is everyone? We've pointed our telescopes at the sky, listened for signals in the static, mapped thousands of stars. Yet there are no obvious cosmic travelers, no wormhole entrances glowing in the dark, no unmistakable footprints of galactic traffic. The highways seem empty, silent. This is the Fermi paradox, sharpened to a blade. If the roads are real, why do we stand alone at the intersection? Some scientists suggest wormholes collapse too quickly. The math doesn't allow stability without exotic matter. Others argue that any advanced beings might cloak their travel, disguising wormhole mouths so they look like ordinary black holes. To us, a collapsed star. To them, a bustling gateway. But there's another, darker possibility. Maybe the roads are dangerous. Imagine civilizations bold enough to step into the tunnel and never return. Maybe wormholes don't lead to distant galaxies but to broken geometries, places where physics itself unravels. In that case, silence isn't absence. It's a graveyard. Yet, silence can also mean caution. If travel is possible, would you advertise it? Wouldn't you hide it, especially from a species just learning fire compared to your mastery of stars? And so we're left with a tension. The highways may be there, unseen, and the silence may not mean emptiness, only that the travelers have learned to move quietly. Picture this. NASA announces they've found a stable wormhole at the edge of our solar system, a tunnel of space itself, sitting out there like a cosmic doorway. How would humanity react? Would it be like Columbus staring across the Atlantic, driven by hunger, fear, and ambition? Or would it be more like staring into a dark cave, wondering what claws lurk inside? Governments would scramble. Military strategists would imagine wormholes as weapons, a shortcut for fleets, or a trap to spring on enemies. Scientists would dream of exploration, exoplanets reachable in a single step, galaxies no longer out of reach. Economists would whisper about minerals, resources, entire new worlds. But here's the catch. Would we dare enter? Because stepping through wouldn't just be travel, it would be irreversible risk. We wouldn't know if the tunnel is stable, or if it snaps shut like a mousetrap once we cross. And then comes the deeper fear. What if something steps out first? Maybe the reason for silence isn't because the roads are empty, but because the owners of those roads guard them carefully. Suddenly, the discovery isn't just about exploration, it's about survival. Humanity would stand at the mouth of the tunnel, debating not only who goes in, but whether to close it forever. Here's the first brutal truth. Wormholes, as Einstein's equations describe them, aren't empty tunnels. They're pressure cookers of gravity, energy, and distortion. Step inside one unprotected, and you wouldn't even have time to scream. Your atoms would stretch, scatter, and dissolve into radiation. So, if humanity ever dared to enter, survival would hinge on engineering the impossible. Physicists suggest we'd need exotic matter, a material with negative energy density, to prop open the wormhole walls and stop them from collapsing. Without it, the tunnel would pinch shut faster than the blink of an eye. But let's imagine for a moment that we succeed. You're inside. What would it feel like? Would time flow normally, like a hallway, or would minutes stretch into centuries? Some models suggest clocks inside a wormhole might tick at bizarre rates compared to the outside universe. You could leave Earth in 2050 and return to find it's the year 1450. And even if you made it through intact, what if the other side opened not into a star system, but into the heart of a black hole? A wrong exit point, and your heroic leap becomes instant annihilation. This isn't just science fiction. These are the stakes written into Einstein's mathematics. A wormhole isn't just a door, it's a razor's edge between discovery and oblivion. For decades, black holes were painted as cosmic monsters, devouring stars, crushing light, erasing information. But in the quiet corners of physics, some dared to ask a heretical question. What if they aren't endings, but beginnings? Picture this. At the event horizon, the very edge of a black hole, space-time doesn't just fall inward. Some models whisper that it could fold outward. Instead of a dead end, the singularity might connect to another region of the cosmos. In essence, a black hole could be half a wormhole, and somewhere else in the universe, a white hole, the mirror opposite, spewing matter and energy instead of swallowing it, might be the exit. It sounds fantastical, but here's the kicker. Black holes already bend time. A spacecraft orbiting near one wouldn't just see the universe racing ahead outside, it might ride the curvature itself. To a bold explorer, a black hole could be not just a prison, but a pathway. But, and this is a devastating but, even if black holes are gateways, the journey in would be one way. The tides of gravity inside would shred matter beyond recognition before it ever reached a hypothetical exit. To survive, we'd need physics that doesn't yet exist, technology that could tame the beast without being devoured by it. So the riddle remains. Are black holes the locks to a hidden network of cosmic highways, or just the ultimate traps? If black holes really could bend space and twist time, another problem emerges, one that isn't about fire or crushing gravity, but about logic itself. What happens when time loops back on itself? Physicists call it the grandfather paradox. Imagine you step through a black hole, travel backward in time, and accidentally prevent your own grandparents from meeting. If they never meet, you're never born. But if you're never born, how did you step through the black hole in the first place? The logic folds in on itself, a paradox without an escape hatch, and yet, nature might be wiser than we give it credit for. Some theories suggest the universe enforces consistency loops. In other words, if you go back, you can't actually change anything important. You could travel through time, yes, but every action you take would already be baked in to history. You might nudge events, but never rewrite them. Others argue the opposite, that stepping through a black hole could branch reality itself. Instead of one fixed line, time could split like the limbs of a tree. Change the past in one branch, and the universe creates a new timeline, while your original one marches on unaffected. But here's the chilling thought. Black holes don't just test physics, they test causality, the very order of cause and effect that our lives depend on. If they are doors into time, they could force us to confront whether the universe is one story or an infinite library of parallel ones. If time paradoxes are so dangerous, maybe that's why we haven't seen any time travelers. Maybe the universe itself has built-in defenses, cosmic laws that prevent reality from tearing apart. One idea comes from physicist Stephen Hawking. He called it the chronology protection conjecture. The name sounds grand, but the meaning is simple. Nature doesn't allow time machines. Whenever conditions arise that might create closed time loops, such as those near black holes or wormholes, something always intervenes. That something might be quantum chaos. As soon as a time loop tries to form, tiny fluctuations at the quantum level could swell into violent storms of energy, shredding the loop before it ever stabilizes. Imagine the universe throwing up roadblocks, invisible barriers saying, "No further, time travel ends here." But others argue this isn't a lock, just a lockpick waiting to be found. What if black holes are not forbidden shortcuts, but carefully guarded gateways? They wouldn't just fling you across space, but across eras, provided you find the right conditions and survive the crossing. And that's the real tension. Are black holes nature's doorman, slamming shut to preserve order? Or are they hidden keys, scattered across the cosmos, waiting for civilizations advanced enough to turn them? If the universe is protecting its secrets, then the question becomes, can intelligence outwit the gatekeepers? Physicists have toyed with the idea that an advanced civilization, perhaps millions of years ahead of us, might find ways to tame a black hole, not to destroy it, not to escape it, but to shape it. Imagine wrapping a black hole in powerful electromagnetic fields, or threading it with exotic matter that prevents collapse. The goal? To stabilize a wormhole inside its core, a tunnel not only through space, but across time. If Hawking's protections are the locks, this would be the master key. But here's where it gets cinematic. Even if such a feat were possible, the energy required is almost unthinkable. We're talking about the power of entire stars, harnessed and bent to human or alien will. A civilization capable of this wouldn't just be advanced. They'd be operating at a scale beyond anything we've ever imagined. Perhaps a Type 2 or Type 3 civilization on the Kardashev scale, commanding the energy of galaxies. And if they could do it, time travel wouldn't be fantasy anymore. Black holes would become machines of destiny, doorways, not prisons. But this opens a haunting new question. If time travel is possible, why haven't we met its travelers? Are they hiding, or are we simply too early in the story to notice? If black holes can be bent into machines of time, then the strangest mystery isn't how, it's why no one seems to be using them. This silence has been called the time travel paradox of the Fermi paradox. The logic is simple. If even one civilization cracked the code, we might expect to see footprints in history. Visitors, messages carved into ancient stone, signals designed to stand out across time, and yet, nothing. But maybe that silence is the answer. What if travelers follow a code, an unwritten prime directive, forbidding them from altering the timeline of less advanced civilizations? They might be watching, quietly, just beyond the veil, invisible until we're ready. Or perhaps the act of traveling back changes the past so profoundly that we never notice the visitors. Each time loop rewrites the record, erasing the evidence as if it never happened. A self-healing history, constantly edited by the very act of time travel. And then comes the unsettling possibility. Maybe we're living in one of those edits. The universe we know, the timeline we trust, could already be the byproduct of travelers long gone. their fingerprints hidden in the cracks of reality? If so, the silence isn't proof that time travel doesn't exist. It's proof that it's already been used, and we are standing inside the rewritten story. What if the universe itself allows for shortcuts, not through machines, not through alien intervention, but through the raw geometry of space-time? Einstein's equations whisper a strange truth. Under the right conditions, space-time can fold into closed, time-like curves. These are loops in reality where a particle, or even a person, could travel forward only to arrive back where they began. Not just in space, but in time. In the 1940s, mathematician Kurt Gödel discovered one such solution while exploring Einstein's field equations. A rotating universe, he showed, could twist space-time into endless circles, making time loops not just science fiction, but mathematics on paper. Imagine a universe where every moment inevitably folds back on itself, where the future is as inevitable as the past. Physicists have wrestled with this idea ever since. Could black holes, with their immense rotations and warping power, act like the gateways Gödel described? Could they be the time doors that nature has hidden in plain sight, waiting for us to unlock? Of course, this raises an unsettling question. If loops are possible, does free will exist at all? Or are we simply passengers, forever riding the same cycle, mistaking repetition for choice? Maybe the silence of time travelers isn't silence at all. Maybe it's us, trapped in loops so perfect that every question, every discovery, every doubt is destined to repeat. If black holes or space-time loops could be doorways to the past or the future, then what would it take to actually step through? Here's where physics gets daring. To stabilize a time tunnel, Einstein's math tells us you'd need something utterly alien, negative energy. Not ordinary matter, not even the dense mass of a star, but a substance that behaves as though it resists existence itself. This isn't fantasy. In quantum physics, strange fluctuations create fleeting regions where negative energy does appear. It's called the Casimir effect, a subtle push between two metal plates in a vacuum caused not by matter, but by the restless vacuum of space. For a brief moment, the universe seems to owe energy, and the rules bend. Now imagine amplifying this ghostly effect to cosmic proportions. Could negative energy line the walls of a wormhole, preventing it from collapsing? Could it make a passage stable enough for something, or someone, to travel through? But there's a catch. Negative energy isn't just rare, it's dangerous. Too much, and physics warns of paradoxes so severe that reality itself might rebel. Some theorists suggest the universe has a kind of cosmic censor, forbidding any timeline that would break causality. In other words, the laws of physics might allow you to build a time machine, but they won't let you use it without consequence. So we are left with a paradox of our own. The fuel for time travel exists in whispers all around us, written in quantum effects and black hole horizons. But to use it may mean tearing at the very fabric of causality, and perhaps waking a universe that does not want to be challenged. But even if we could tame the exotic fuel of negative energy and hold a wormhole open, there's a deeper problem waiting for us. Not a technical problem, but a logical one. Physicists call it the grandfather paradox. Imagine you step through a time tunnel, traveling back to an era before you were born. Suppose you interfere in the smallest way, even something as absurd as preventing your grandparents from meeting. Suddenly your own existence unravels. But if you were never born, then who traveled back to change the past? It sounds like a riddle, but it isn't just philosophy. In physics, paradoxes signal that a theory might be incomplete, or that nature itself enforces limits. Some argue the universe has a built-in safeguard, ensuring events always weave together into a consistent timeline. This is known as the Novikov self-consistency principle. It suggests that no matter what you do, your actions in the past will always fold seamlessly into the history that already exists. Others disagree. They point toward the eerie possibilities of many worlds. In this picture, stepping into the past doesn't change your own history, it splits it. Every choice you make creates a branching timeline, one where your grandparents never meet, and another where they still do. You don't erase your own existence, you create a new strand of reality. And here's where the story turns from science to something almost mythic. Time travel may not just test our machines or our mathematics, it may test the very structure of reality itself. Are we locked into a single, unbroken history? Or do our choices carve an endless forest of parallel worlds? If the universe refuses paradox, then maybe it takes a more daring path. Perhaps every impossible choice, every contradiction, is solved by branching reality itself. This is the heart of the many worlds interpretation of quantum mechanics. In the quantum realm, particles don't exist in just one state. They hover in probabilities. A particle can be here and there, spin up and spin down, until it is observed. To most physicists, this collapse into a single outcome is just part of the mystery. But others argue the wave never collapses. Instead, every possible outcome happens, each in its own newly split universe. Now imagine applying that logic to time travel. Step into the past, alter one moment, and you don't erase your own history. You simply create another. In one branch, your grandparents still meet and you exist. In another, they don't, and someone else lives a very different life in your place. Both universes are real, forever running in parallel. It sounds like science fiction, but quantum experiments already hint at this strangeness. Electrons behave as if they are exploring multiple paths at once. Photons interfere with their own ghostly twins. And some researchers argue that the mathematics of quantum theory makes the many worlds unavoidable. But if that's true, then time travel may not let us rewrite history. Instead, it could make us wanderers, crossing from one branch of the cosmic forest to another. And that raises a haunting question. If countless versions of reality already exist, what happens if a time traveler meets not their past self, but another self who was always meant to exist in a different universe? If alternate timelines are more than a thought experiment, shouldn't there be hints, faint cracks in reality where the branches brush against each other? Physicists hunting for those cracks have turned to the quantum world. Here, particles seem to do the impossible. In experiments like the delayed choice quantum eraser, a photon can behave as if it knew the decision of an observer after it traveled. Cause and effect, the bedrock of time itself, suddenly looks negotiable. In another experiment, scientists sent entangled particles racing in opposite directions. What one particle chose instantly determined the fate of the other across vast distances, faster than light itself could travel. Einstein scoffed at this, calling it spooky action at a distance. But to some, it looks like a faint echo of time travel, information slipping outside the normal flow of cause and effect. And then there's the strangest twist. Some quantum equations allow for closed time-like curves, mathematical loops where particles might interact with their own past selves, not in grand DeLorean arcs, but in tiny, fleeting nudges of information, a whisper traveling backward, correcting itself, like reality rehearsing a line until it gets it right. These are not science fiction fantasies. They are real experiments, published in peer-reviewed journals, debated fiercely in physics departments. And though no one has built a working time machine, the universe itself may already be playing with time's rules in miniature. Which leaves us with an unnerving question. If particles can cheat time in subtle ways, what would stop a civilization, millions of years ahead of us, from amplifying that trick into something we'd recognize as a time machine? If quantum particles bend time in whispers, black holes shout it in thunder. Imagine a star so massive that its death collapses space into a pit no light can escape. At its edge, the event horizon, time itself slows to a crawl. To an outside observer, anything falling in seems to freeze, stretched like a ghost, never quite crossing. But to the falling traveller, time ticks on as normal, their plunge unstoppable. Einstein's equations predict this time dilation with eerie precision. Near a black hole, minutes for you might be centuries for someone watching from a safe distance. Time fractures becoming relative, personal, elastic, and deeper still, in the black hole's core, lurks the singularity, a place where space and time fold so violently that our mathematics fail. Some physicists whisper that singularities might hide wormholes, tunnels that connect distant regions of space, or even different times. Carl Sagan once asked Kip Thorne, one of the world's experts in relativity, whether such wormholes could be stable enough for travel. Thorne's answer, maybe, but only with exotic matter to keep them open, matter that bends gravity in reverse, like scaffolding holding up a tunnel through time. This isn't science fiction scribbling, it's hard math, checked again and again. Black holes are not just destructive, they may be portals, testing grounds where time itself reveals its seams. But if the universe already builds such engines, why haven't we seen travelers emerge? Is it because they never existed, or because they know better than to reveal themselves? The idea of black holes as time machines sounds irresistible. But here's the catch. They are not gentle gateways, they are violent arenas. Picture approaching a stellar mass black hole. The gravity gradient, the difference between your head and your feet, would stretch you into spaghetti. Scientists literally call this spaghettification. For a human traveler, it's a death sentence long before time travel could even begin. But physicists don't stop there. They ask, what about supermassive black holes? These giants, millions or billions of times the mass of our sun, have gentler tidal forces at their horizons. In theory, you could cross without immediate destruction. Time would slow for you relative to the universe outside, and perhaps, just perhaps, you could survive long enough to test what lies beyond. And here's where speculation tilts toward the extraordinary. Some models suggest rotating black holes, Kerr black holes, could create stable pathways, looping time back on itself like a cosmic knot. In equations, these look like gateways, offering exits not just across space but across centuries. But the math also screams warnings. The slightest disturbance, the tiniest photon of energy, could collapse the passage. A portal one moment, a crushing singularity the next. Nature may tease us with the possibility of time travel, only to snatch it away at the brink. Still, the thought lingers. If a civilization advanced enough could harness a Kerr black hole, could they bend time at will? And if so, would we ever know they had done it? Or would we only see their fingerprints in strange anomalies? Deja vu moments written across the cosmos. If black holes really could serve as time machines, we should ask, would there be evidence? Astronomers already find strange footprints across the universe. Consider quasars, those dazzling beacons at the edge of the observable cosmos. Powered by supermassive black holes, they shine brighter than entire galaxies. Yet some flicker with eerie regularity, as if pulsing to a rhythm written beyond time itself. Could those pulses be natural, or echoes of something tampering with space-time itself? Then there are fast radio bursts, sudden millisecond flashes of radio energy appearing and vanishing without warning. To mainstream science, they are extreme astrophysical events. But in the more speculative corridors of physics, they're imagined as time pings, signals generated when something brushes against the edges of a temporal gateway. And here's the hook. Every black hole, in theory, stores a record of everything it consumes. Not destroyed, but scrambled. If time travel is possible, perhaps these records aren't just locked inside forever. Perhaps they can leak out like whispers from the past, clawing their way back into the present. It sounds fantastical, yet it folds into real debates in physics. The information paradox, championed by Stephen Hawking, asks whether black holes truly erase information. The resolution might hint at whether time itself can recycle events, or whether once something is gone, it is gone forever. So maybe the universe has already tried time travel. Maybe we are looking at the side effects every time we notice a pattern that doesn't quite fit, a cosmic rhythm we cannot yet decode.
If the universe leaves hints that time travel might be possible, the next question is unavoidable. Could humans themselves ever step through one of these cosmic doors? Imagine it, not just observing black holes from afar, but approaching one with purpose, a ship designed not to orbit safely at the edge, but to dive. To attempt what sounds impossible, surfing the very geometry of space-time. Here, physics divides into two voices. The cautious one says, no, never. The tidal forces near a black hole would tear any craft, and its occupants, apart atom by atom. The more optimistic voice counters, perhaps not all black holes are equal. A rotating black hole, known as a Kerr black hole, might provide a narrow, stable corridor through space-time, where gravity does not crush but curves smoothly, like a tunnel carved into the fabric of reality. Science fiction turns that idea into starships disappearing into dark spheres, only to reappear centuries earlier, or later, across the universe. But here's the twist. It's not just fiction. Real equations derived from Einstein's relativity suggest those corridors could exist under very precise conditions. Yet the practical barriers loom. How would we shield a craft from radiation near the event horizon? How would we even navigate a pathway where time and space no longer behave in any intuitive way? Each challenge feels insurmountable. And yet, history is full of human leaps once thought impossible. Flight, space travel, splitting the atom. So we return to the most tantalizing thought of all. Maybe it isn't about whether time travel is possible. Maybe it's about whether civilizations live long enough or dare boldly enough to try. But suppose for a moment humanity actually succeeds. Suppose some future generation builds a ship, dives into a rotating black hole, and emerges not just elsewhere in space, but elsewhere in time. That's when physics runs headlong into philosophy and into paradox. The most famous is simple, almost childlike in its clarity, the grandfather paradox. If a traveller goes back and prevents their own ancestor from surviving long enough to have children, how could the traveller exist in the first place? It's a knot with no loose ends to pull free. But here's the twist. Relativity itself doesn't forbid time loops. Instead, some physicists suggest the universe may protect itself from paradoxes. This is the Novikov self-consistency principle, the idea that any action taken by a time traveller was always part of history to begin with. In other words, you can go back, but you cannot change what already is. Shoot the gun and the bullet misfires. Shout the warning and it is ignored. The past bends to prevent contradiction. And yet, there's an equally bold alternative. The many worlds interpretation. According to this view, every time you change the past, you don't rewrite history. You split it. You step into a parallel branch where your actions unfold freely while the original timeline continues untouched. Save your grandfather, and a new world blooms where you were never born. Destroy the empire, and another universe rises in its place. Both explanations are strange, unsettling, and strangely comforting. Either the universe is self-healing or it's endlessly branching. Either way, time travel might not be the reckless unraveling of reality we fear, but simply another way the cosmos expresses its infinite possibilities. But paradoxes aren't just thought experiments about grandparents and history books. They stretch into something even stranger, the idea of information that has no origin. Imagine a scientist in the far future. She scribbles down the equations for a new technology, say a device that bends space-time itself. But where did she learn it? From an old notebook passed down through generations. A notebook, she later discovers, was hers all along, delivered to her younger self by a traveller from the future. The equations exist, yet they were never invented. They simply loop. This is called a causal loop or bootstrap paradox. Information, events, even objects can become trapped in self-sustaining cycles, existing without a true beginning. A song with no composer, a theory with no discoverer, a message from nowhere that nonetheless defines everything. And it doesn't just belong to science fiction. General relativity actually allows for solutions where these loops could occur. Closed time-like curves, where cause and effect chase each other endlessly around a cosmic racetrack. Here's the unsettling part. If black holes could ever act as gateways, they might be the engines that make these loops possible. A whisper sent through a wormhole could echo forever, bouncing between timelines, guiding civilizations that never truly invented the knowledge they depend on. So we're left with a chilling question. If humanity ever does build time machines, how much of what we think we've discovered might, in truth, be borrowed from ourselves? If knowledge can loop, then the question becomes, who controls the loop? Picture this. A future civilization discovers how to send information through a black hole. Not people, not ships, but ideas. Instructions, blueprints, warnings. Instead of discovering fire, inventing electricity, or building rockets the slow way, they simply gift themselves the answers through time. Overnight, their past accelerates. What should have taken millennia happens in centuries. But here's the catch. If every invention comes from the future, then who truly created it? Did they ever innovate at all, or were they only ever following instructions written by their descendants? Progress becomes a hall of mirrors, every step forward just an echo bouncing back from what's yet to come. Now imagine this not as a human quirk, but as a galactic strategy. Civilizations might compete not only across space, but across time. Some could hoard their future knowledge, keeping their past weak and dependent, while others might flood their history with gifts, rewriting destiny at will. And here's where black holes re-enter the story. If they are more than stellar corpses, if they can link times as well as spaces, then they become weapons, vaults, and communication networks all at once. A civilization with access to such loops wouldn't just dominate planets, they'd dominate eras. Which leaves us with a haunting thought. If humanity is waiting for the great leap, some mysterious breakthrough that feels too advanced, too sudden to be natural, what if it doesn't come from aliens at all? What if it comes from us, whispering to ourselves across the abyss of time? If civilizations could send whispers into their own past, it raises a chilling question. Is the universe itself designed to allow such loops? Mathematicians once played with this idea. In the 1940s, Kurt Gödel, the same mind who shattered mathematics with his incompleteness theorems, proposed a model of the cosmos where time itself curves back on itself. Imagine living not in a straight line of past to future, but in a cosmic carousel where if you travel far enough, you don't reach new moments. You return to the old ones. Physicists call these pathways closed time-like curves. In normal space, if you walk in a circle, you return to where you began. In Gödel's universe, time itself works that way. Move forward long enough and you find yourself back at yesterday. Now, add black holes to the picture. Some equations suggest that near the rim of a spinning black hole, a Kerr black hole, these closed time-like curves might actually exist. Space and time get so twisted that forward and backward blur like ink stirred in water. Could a civilization harness this? Build machines that ride the eddies of time itself? And here's the eerie part. If such loops are possible, then maybe civilizations don't just send knowledge back. Maybe they exist in cycles, living the same cosmic story over and over, tweaking tiny details each time, hoping one version of history finally gets it right. So when we gaze at the stars, maybe we aren't looking at other beings at all. Maybe we're looking at echoes of our own future selves, trapped in an endless return. But if the universe allows loops in time, then comes the problem physicists dread most, the paradox. Imagine stepping through a doorway carved by a black hole's spinning edge and landing in your own past. You meet your younger self. You warn them about a mistake. They avoid it, which means you never had the reason to travel back in the first place. So, who set it all in motion? This is the infamous grandfather paradox. The idea that if you could alter the past, you might erase the very conditions that allowed you to travel there. Physicists like Stephen Hawking thought nature might defend itself from such logical chaos. He called it the chronology protection conjecture. The universe conspires to prevent time loops, shutting them down before they break reality. Yet others argued differently. What if paradoxes never truly occur? Not because time travel is impossible, but because the universe self-corrects. Every action you take in the past is already part of history. If you try to stop your younger self, maybe you fail in exactly the way that ensures the timeline survives unchanged. Black holes make this even stranger. Near their swirling edges, equations hint that quantum probabilities, the same weird dice rolls that govern particles, could dictate outcomes. In one version, you warn your younger self. In another, you don't. Both happen. Both are real. The paradox dissolves, not by prevention, but by multiplying into many histories. So the paradox isn't a wall, it's a fork. And black holes might be the knives that carve the universe into countless timelines. But what if the universe doesn't just protect itself? What if it simply splits? Picture this. You dive through a black hole's warped throat, emerge in the past, and decide to stop your younger self. In your timeline, you succeed. But instead of unraveling the logic of your own existence, the cosmos quietly makes room. A second branch opens. A new universe, identical up until that moment, now forever altered by your interference. This is the many worlds interpretation, first whispered in quantum physics but magnified to cosmic scale by black holes. Every paradox is avoided, not by blocking the act, but by spawning another reality where the act and its consequences unfold. It's an elegant escape hatch. Black holes with their mind-bending geometry might be more than prisons for light. They could be cosmic forges of timelines spilling out alternate histories like sparks from a forge. Think about it. Somewhere, perhaps just one branch away, you never fell into the black hole. In another, humanity never discovered them at all. And in yet another, civilizations may have learned to navigate these splits, not fearing paradoxes, but using black holes as gateways to multiverses. Of course, this raises a haunting question. If black holes are already seeding new universes, are we living inside one of them right now? A timeline birthed long ago by some ancient collapse, carrying us forward on the aftermath of another universe's fall. If a black hole can bend timelines, could it also plant new ones? Physicists like Lee Smolin have suggested something astonishing. Every black hole might be a womb for another universe. Imagine, the crushing singularity at a black hole's heart doesn't just destroy matter. It recycles it, blasting it outward in another dimension, birthing a cosmos with its own physics, its own galaxies, its own story. In this view, our universe may not be the first. We could be the child of a black hole in some older cosmos, a cosmic Russian doll, each universe nested inside another.
And if that's true, then every black hole we see glittering in the night sky may not be an ending, but a beginning. Here's the twist. These baby universes might inherit slight variations in their laws of physics. Some may have weaker gravity, some may lack stable atoms, others may be chaotic, unstable, doomed from birth. But the ones like ours, balanced just right for stars, planets and life, thrive. That means our reality might exist not by chance, but by cosmic natural selection. The universes that can birth black holes go on to have descendants, while barren ones simply fade away. Black holes don't just shape time travel, they may shape the evolution of reality itself. And it leaves us with a chilling possibility. When we stare into a black hole, are we looking at the grave of a star or the cradle of a universe? If black holes really seed new universes, who's to say they can't also be doorways? For us, they're terrifying abysses, regions where light itself is trapped. But imagine a civilization millions of years ahead of ours, a species that long ago conquered their own solar system, drained the energy of stars, and reached the brink of extinction. Faced with the end, what if they turned to black holes, not as tombs, but as escape hatches? Some theorists whisper of universe hopping, the idea that, with enough mastery of physics, a civilization could thread their way past the event horizon not into destruction, but into a new cosmos, one with fresh stars, unburned fuel, and endless futures. It's almost poetic, the dying universe handing its torch to the next. And if this is true, black holes may not just be natural engines of creation. They may also be arcs, ferrying knowledge, DNA, or even entire species across the void of nothingness into rebirth. Of course, to us, this sounds impossible. But then again, to a fish, the idea of leaving water would sound impossible too. Perhaps civilizations far older than us already made the leap. Perhaps our own existence is proof that one of them succeeded. And that raises a question both thrilling and haunting. When we gaze at the dark mouths of black holes, are we only looking at nature's creation, or are we staring at someone else's exit door? But here's the catch. If black holes truly hide escape routes, we have no way to prove it. Our instruments stop at the event horizon. For us, it's a curtain that never lifts. Astronomers have tried to push that curtain aside. With the Event Horizon Telescope, we stitched together the first shadowy images of a black hole. The glowing ring around M87 star, a monster billions of times heavier than our sun. But even then, we're only seeing the edge, the outer glow where matter burns like fire before vanishing. Beyond that, silence. And that silence is what drives both wonder and frustration. Physics tells us the laws we know break down inside. Relativity and quantum mechanics clash like two musicians playing different songs at once. For scientists, black holes are less like cosmic doorways and more like walls. Every experiment, every telescope ends at the same boundary, and yet paradoxically, it is this very blindness that keeps us hooked, because behind those walls might be nothing at all, or everything we've ever hoped for, civilizations traveling through, baby universes inflating, or perhaps just the raw chaos of a physics we'll never tame. So when we stare into a black hole, we're not just looking at space, we're looking at the limits of knowledge itself, and maybe, just maybe, those limits aren't permanent. Maybe those limits aren't permanent. Maybe they're only the walls of a room we haven't yet found the door to. Already scientists are pushing at the edges. The Event Horizon Telescope was just the beginning, a first blurry glimpse. Imagine what happens when the next generation of telescopes comes online. Arrays in space, unhindered by Earth's atmosphere, capturing the faintest ripples of light bent around black holes. And it's not just light we're listening to anymore. Gravitational wave observatories like LIGO and Virgo are eavesdropping on the universe's deepest conversations. When black holes collide, the very fabric of space-time trembles. And in those tremors may be clues, whispers about what lies behind the horizon, or whether wormholes are more than mathematical mirages. This is the frontier where theory meets ambition. Physicists dream of quantum computers powerful enough to simulate black holes to resolve the paradoxes that stump us now. Could information really survive inside? Could the dreaded singularity, that infinitely dense heart, be just a mirage created by our incomplete math? For now, the answers are sketches, not portraits. But the sketches are growing sharper, and each year we add another brushstroke to the cosmic canvas. Because humanity has always been restless. And if history teaches us anything, it's this. Every boundary we've declared final, the sound barrier, the edge of the map, the limits of the atom, has eventually been crossed. So the question becomes, who will be the first to cross this one? Who will be the first to cross this frontier? A lone scientist? An international team? Or perhaps not a human at all? Because here's the truth. Our bodies are fragile. Radiation, gravity, and time itself conspire against us. But machines? Machines don't age. They don't need air, food, or sleep. Already, probes like Voyager have outlasted entire generations, drifting farther than their creators ever imagined. Now imagine a new kind of explorer. Artificial intelligences housed in hardened shells, capable of thinking faster than any human mind, sent not to orbit black holes from afar, but to skim their very edges. They could measure distortions in space-time with precision no human could endure, sending back data that might finally answer the questions Einstein and Hawking only dreamed about. Would such machines be our scouts, whispering to us from places no living human will ever go? And yet, history suggests we won't be satisfied with only listening. Humans are stubbornly curious and reckless. The same species that climbed Everest because it was there, that sailed into oceans they believed might boil, will one day look at a black hole and feel the pull to get closer. The first pioneers may not set foot beyond the event horizon, but they will stand at the threshold, daring to test the boundary. And when they do, the line between science and legend may blur forever, but standing at the threshold comes with a price. Radiation, invisible and merciless, streams from the swirling accretion disk like a storm of bullets. One miscalculation and a probe, or a human craft, could be torn apart atom by atom. Then there's the crushing tidal pull, the infamous spaghettification, where even molecules are stretched into threads thinner than silk. To linger too long near the horizon is to risk becoming part of the black hole itself. And yet, the most unsettling danger may not be destruction, but distortion. Imagine sending a probe toward the edge, watching it tick, record, transmit. From Earth, its signals slow, its heartbeat drawn out until silence. Did it cross the horizon, or is it still there, frozen in time from our perspective? For the pioneers, time may run normally, seconds, minutes, hours, but for those watching back home, entire centuries could pass. This is the paradox at the edge of reality. What looks like a fatal pause from one vantage point may, from another, be the start of a journey deeper than anything humankind has ever attempted. The cost of curiosity may be not just lives or machines, but the very separation of explorers from the world they left behind. And yet, history tells us something profound. Every great leap forward has come at the edge of sacrifice. The first sailors who vanished into unknown seas, the test pilots who flew faster than sound, the astronauts who sat atop rockets built on hope and calculation, none could be certain they would return. Standing at the rim of a black hole may be the same. Probes will be lost. Data will be cut off mid-transmission. Crews, if ever they dare, may vanish into silence. But sometimes silence is its own kind of revelation. If a probe disappears and never returns, that in itself confirms what theory has long whispered. The event horizon is absolute. If it lingers, frozen at the edge for centuries, it tells us time itself bends to the black hole's command. And if, impossibly, signals return from within, distorted but decipherable, then everything we thought we knew about physics would shatter. In that silence, humanity may find not just loss, but knowledge. For it is only in pushing against the limits of the impossible that the universe reveals its deepest secrets. And black holes, strange as they are, may hold the key not only to understanding time, but to travelling through it. So imagine for a moment that the silence is broken. A probe edges close, survives longer than expected, and its instruments confirm what Einstein's equations have been whispering for more than a century. Black holes don't just swallow space, they bend time itself. To an outside observer, that probe seems to freeze at the horizon, forever suspended in a cosmic pause. But to the probe itself, time ticks on normally. Hours pass, days, perhaps even years. When, or if, its signal emerges again, it may return carrying not just data from the edge of eternity, but proof that time has flowed differently for it than for us. This isn't science fiction. General relativity predicts that gravity warps time. On Earth, GPS satellites must constantly adjust their clocks to match the planet's weaker gravitational pull. Near a black hole, that effect isn't subtle, it's extreme. Minutes spent near the event horizon could equal centuries passing in the wider universe. And suddenly, the black hole isn't just a devourer of worlds. It is a one-way vessel into the future, not by magic, but by the very structure of space-time. To orbit a black hole and return is, in theory, to leap forward in time, to leave behind the world you knew, and return to a future where everything has changed. Picture this: a lone astronaut, tethered to their vessel, skims the edge of a black hole. From their perspective, nothing unusual happens. They check their oxygen, record their notes, and watch the steady ticking of the onboard clock. An hour drifts by, 2, maybe 3, but when they finally fire the thrusters, breaking free of the black hole's grip and returning to open space, the universe they left behind is unrecognizable. To them, only a few hours have passed. To Earth, centuries. Civilizations may have risen and fallen. Entire generations have been born, lived and died. This isn't fantasy. Einstein's equations demand it. We see hints of this truth even today. Astronauts aboard the International Space Station experience a fraction of a second less time than we do on Earth, thanks to their speed and orbital altitude. Near a black hole, that tiny fraction swells into gulfs of time. And so, the black hole becomes not just a cosmic abyss, but a bridge into tomorrow. Step too close, and you become a traveller into the far future, not by choice, but by physics. It's a haunting thought. You could leave your loved ones behind for what feels like an afternoon, and return to find them long gone, their world a memory only history remembers. But if black holes can send us into the future, could they also, in some way, take us back into the past? That question is where speculation turns bold, and where imagination dares to outpace even science. Up to now, the science has carried us in one direction: forward. The equations of relativity, the stretching of time near gravity wells, the experiments with speeding particles, all of it agrees the future is accessible. Step into the right conditions, and time itself slows for you, letting centuries pass in the blink of an eye. But what about the other way? Could a black hole, or something stranger still, let us reverse the arrow of time? It feels almost sacrilegious to ask, because here's the truth. Going backward is where the universe begins to resist us. Einstein's equations do allow for closed, time-like curves, strange loops in space-time where, at least on paper, you could circle back to your own past. And in some interpretations, spinning black holes, Kerr black holes, create just such a region where the very fabric of time might twist into loops. But the dangers are immense. Physicists call it the grandfather paradox. If you travel back and alter even the smallest detail, meet your younger self, change a decision, move an atom from its destined path, the consequences ripple outward. Cause and effect become scrambled. Logic itself seems to fracture. And yet, the temptation is too great to ignore. The idea that a black hole, already bending space into impossible knots, might also bend time into a circle, is one of the most tantalizing puzzles in modern physics. So here lies the question. Are these backward doors to time merely mathematical mirages, or might nature have hidden them inside the darkest hearts of the cosmos? If time can bend backward, even just in theory, then we are forced to wrestle with puzzles that sound more like riddles than physics. Imagine this. You travel through a loop in space-time, step out of the black hole's twisted geometry, and arrive in your own past. Now comes the grandfather paradox. Could you change something so fundamental that it would prevent your own journey in the first place? What if, by accident or design, your actions erase the very chain of events that brought you here? Logic collapses in on itself, a kind of intellectual black hole. But there's another twist, the bootstrap paradox. Imagine carrying a notebook of equations with you into the past. You hand it to a young Einstein who publishes them, and those very equations inspire the discoveries that led to your journey. But then, who wrote them first? You, Einstein, or were they always floating in a self-created loop? Physicists don't just dismiss these as science fiction puzzles, they've tried to solve them. Some argue that the universe forbids paradoxes outright. This is called the Novikov self-consistency principle. In this view, the laws of physics prevent you from altering the past in any way that creates contradiction. You can travel back, yes, but you cannot change anything. You would find yourself trapped in a story where every choice you make was always part of the past. Others imagine a multiverse solution. Every paradox spawns a branch. You go back and change history? Fine. But that change simply splits reality, sending you into a new timeline while your original remains intact. And here's where the mystery deepens. Is the universe a single, self-consistent reel of film, unchangeable and eternal? Or is it an infinite branching tree, each choice opening new futures, each paradox birthing new worlds? The black hole doesn't answer. It only asks the question louder. The paradoxes may sound like brain teasers, but physics gives them teeth through one of the strangest creatures in the cosmos, the Kerr black hole. Unlike the static monsters we usually imagine, Kerr black holes spin, and in their spin lies possibility. Picture it. A massive star collapses, but instead of forming a motionless singularity, it retains its angular momentum. The result is a black hole whirling at incredible speeds, dragging space-time itself into a cosmic whirlpool. This region, known as the ergosphere, doesn't just pull in matter and light, it twists the very coordinates of time. Mathematically, solutions to Einstein's equations suggest that Kerr black holes could harbour closed, time-like curves, paths that bend backward through the fabric of time itself. These curves are the skeleton keys to the paradoxes we just explored. Step into the ergosphere, circle the singularity, and in theory you could re-emerge in your own past. Not through magic, but through geometry. Time would not be an arrow, but a circle. But here's the catch. Reality may not be so forgiving. The mathematics that permit such curves also permit instability. Tiny fluctuations, Even a single photon could destabilize the loop, shredding it before anyone could ever ride it. Physicist Kip Thorne once described it as nature's censorship, a built-in guardrail preventing humans from rewriting history. Yet, the Kerr solution refuses to vanish. Every time physicists test Einstein's equations, this possibility reappears, lurking like a shadow. It whispers, if the universe permits such an engine, does it mean backward time travel is not only possible, but inevitable? And just as that question burns, another rises. If Kerr black holes are engines of time loops, are they already being used? If Kerr black holes are the engines of time loops, then stepping near one would be like boarding a ship without knowing if the ocean ahead is water or fire. The ergosphere promises possibility, but it is also a furnace. Here, matter and energy don't just fall in, they are stretched, shredded, and superheated. Radiation floods the region, making it one of the most violent environments in the universe. For any traveller, shielding against this storm would be the first impossible hurdle. Then comes the geometry itself. Closed time-like curves exist on paper, but the real universe is never so pristine. Even a tiny ripple, a stray particle, a single photon, could destabilize the curve, unraveling the loop before it completes. Physicists call this chronology protection, a kind of cosmic immune system that prevents paradoxes by destroying the very conditions that would create them. And if that wasn't enough, there's the singularity itself. In the Kerr model, it isn't a point but a ring of infinite density spinning endlessly. Cross its path and space-time doesn't bend, it breaks. Equations lose their meaning. The laws of physics fall silent. So while the math teases us with circles in time, the reality seems hostile, almost as if the universe has rigged the game. Nature tempts us with the possibility of rewriting history, and then slams the door shut. But here's the mystery. Doors shut to us might still be open to someone else. If the laws of physics allow Kerr black holes to host loops, what's to say a sufficiently advanced civilization hasn't already learned to tame them? If the universe guards its secrets with fire and fury, what kind of mind would dare unlock them? Some physicists speculate that an advanced civilization, thousands or millions of years beyond us, could already manipulate Kerr black holes the way we manipulate magnets or electricity. Imagine a species that treats singularities as tools, not threats. They could shield themselves from deadly radiation with technologies we can't even dream of, perhaps bending space itself to redirect the storm. They could stabilize time-like loops the way we stabilize bridges or satellites, smoothing ripples before they tear space-time apart. The idea isn't just science fiction. The Kardashev scale, a way of measuring civilizations by their energy mastery, suggests that a Type 2 or 3 civilization, one that harnesses the full energy of stars or galaxies, would view black holes not as monsters but as engines for power, for travel, and maybe for time. And here's the haunting thought. If time loops are real, we wouldn't know if someone else was already using them. Their journeys could thread through history silently, unseen, altering events in ways so subtle we'd never recognize them. What looks to us like an impossible paradox may, to them, be a carefully maintained cycle. Invisible to human eyes, but obvious to beings who see time not as a line but as a landscape. But before we let our imaginations run too far, we have to face the walls nature has built around us. Every time physicists sharpen the equations of general relativity, the same warnings appear. Causality violations, runaway feedback, infinite energy demands. Take the problem of radiation. Inside a spinning black hole, the energy swirling around the event horizon doesn't behave politely. It feeds on itself, like a microphone squealing when it gets too close to a speaker. This blue shift effect grows without limit. until any hypothetical traveller would be obliterated in a storm of infinite heat and light. Then there's the paradox problem. If a time loop allows you to change events, logic itself collapses. Could you prevent your own launch into the black hole? Could you stop the very civilization that invented the technology? To physicists like Stephen Hawking, this isn't just a curiosity, it's a deal breaker. He called it the chronology protection conjecture. The universe itself conspires to prevent time machines from ever forming. And even if somehow the math allowed it, the engineering cost would be staggering. Stabilizing a black hole would require energy greater than what entire galaxies produce just to keep the loop from tearing apart. For us, it's like trying to run a power grid on candlelight. So while our minds can wander to civilizations gliding through history, the reality is sobering. The universe seems determined to shut the door before it ever opens. And yet, nature rarely builds a wall without leaving cracks. While relativity slams the door on classical time travel, quantum mechanics quietly whispers alternatives. In the quantum world, certainty dissolves into probabilities. Particles don't just exist in one place, they smear across possibilities. Some physicists have wondered, could this uncertainty smooth over the contradictions of time travel? Instead of preventing paradoxes, maybe the universe sidesteps them by splitting reality itself. This idea is called the many worlds interpretation. Picture it. You enter a black hole's time loop and shoot an arrow into your own past. In one branch, the arrow hits its target, altering history. But in another, untouched branch, events continue as they always did. Both futures exist. Both are real. The paradox evaporates because no single timeline has to remain consistent. Others propose stranger loopholes still. Quantum fluctuations, tiny tremors in the vacuum, might allow micro wormholes to form, collapsing and reforming in the blink of an eye. What if a sufficiently advanced intelligence could stabilize one? What if quantum uncertainty itself is the bridge, not the barrier? These ideas sound fantastical, but they rest on equations taken seriously in physics departments around the world. They remind us that the line between impossible and undiscovered is thinner than it looks. So even as Hawking's chronology protection warns us away, quantum theory raises its hand and asks, but what if? But theories alone aren't enough. Physics doesn't live on paper. It demands experiments. And in the quiet corners of laboratories around the world, researchers have begun probing whether quantum mechanics and gravity might actually shake hands. Take the LHC, the Large Hadron Collider. Buried under the border of France and Switzerland, it smashes particles together at energies rivaling those of the early universe. Some predicted that if microscopic black holes could form, the LHC might briefly create them, and with them the tiniest portals to strange physics. None have appeared yet, but the search continues, sharpening our understanding of spacetime's fabric. Then there's the work on quantum entanglement. Two particles separated by miles can behave as though they're linked by an invisible thread. Einstein called it spooky action at a distance. If entanglement ignores space, could it also ignore time? Could one particle talk to its partner not just across a room, but across centuries? Even light itself has been enlisted. Physicists fire laser beams into exotic crystals and watch how they scatter, hoping to glimpse evidence of space-time foam, tiny fluctuations that may hint at hidden dimensions or wormhole-like behavior on unimaginably small scales. Each test is like knocking on the universe's locked doors, waiting to see if one rattles open. So far, the locks have held. But history reminds us, every revolution in physics, relativity, quantum mechanics, cosmology, began with experiments that seemed absurd until they weren't. Even as scientists tested colliders and crystals, our species was busy exploring time in another laboratory, the human mind. Long before Einstein's equations bent clocks, authors and dreamers were already bending centuries. Think of H.G. Wells' The Time Machine. written in 1895 when physics still thought the universe was an endless clockwork. Wells didn't just invent a machine, he invented a way of thinking. He dared his readers to imagine that the future wasn't fixed, that the past might be revisited, and that time was a landscape to explore, not a current to endure. Centuries earlier, ancient myths told of heroes who left their villages, only to return and find decades had passed. The Japanese legend of Urashima Taro, the Irish tale of Oisin, even stories whispered in Indian texts, all echoed the same eerie theme. What if stepping outside the flow of time was possible? What if one day felt like a lifetime? And cinema took these seeds and magnified them. From Back to the Future to Interstellar, from light-hearted paradoxes to heart-wrenching dramas, time travel became more than entertainment. It became a mirror, reflecting our deepest hopes, to undo regrets, to glimpse tomorrow, to outwit death itself. But here's the fascinating part. As fiction played with paradoxes, physicists took notice. Wells' imagined machine planted the seed of asking, what if this could be real? Sometimes the border between science and story isn't a line, it's a dialogue. And that dialogue is still ongoing, because the more we tell tales of time travel, the more we ask the very question scientists are still testing in colliders and equations. What if? While storytellers wove myths of lost years and futuristic machines, physicists began sketching a different kind of story, one written not in words but in geometry. Because time, Einstein showed, isn't just a ticking clock, it's a dimension woven into space itself. Imagine bending a sheet of paper until its edges touch. To an ant crawling along the surface, two distant points have suddenly become neighbours. Einstein's equations hinted that the same could be true of the universe. Space-time itself could fold, twist, or loop back on itself. This is where the idea of closed, time-like curves comes in. Pathways through space-time that don't just move forward, but circle back, allowing someone or something to revisit their own past. The great mathematician Kurt Gödel even proposed a rotating universe where time itself swirls like a whirlpool, offering paths back to yesterday. But here's the catch. These solutions aren't fantasy. They're real mathematical possibilities lurking in Einstein's field equations. To physicists, it was as if the universe whispered, time travel might not be impossible. It might just require the right geometry. And so the dream of travelling back, not just forward, shifted from folklore to formula. Suddenly the question wasn't whether humans imagined time travel. It was whether nature herself had written it into the code of reality. But if those loops exist, what do they mean for cause and effect? Could someone truly step into yesterday and change it? Or would the universe fight back? But if space-time can bend back on itself, letting you step into yesterday, a thorny question leaps forward. What happens to cause and effect? Picture this. A traveller goes back in time and prevents their grandparents from meeting. The so-called grandfather paradox. If they succeed, they erase their own existence. But if they never existed, who went back in time in the first place? Physicists love to wrestle with these riddles because they're more than thought experiments. They force us to confront whether the universe is consistent, whether reality allows contradictions, or whether it has built-in safeguards. One possible safeguard: consistency constraints. The idea that no matter what you do, events will always twist themselves to preserve history. If you try to stop your grandparents meeting, some accident, some coincidence will intervene. You might drop the note, miss the train, or accidentally set up the very moment you were trying to prevent. Another possibility? Parallel timelines. Instead of contradictions, every action spawns a new branch of reality. Kill the past version of yourself, and you've only created a different universe where you never existed. while your original timeline marches on untouched. And so the paradox isn't a dead end, but a fork in the road. Does the cosmos demand consistency, or does it endlessly branch into multiverses? From here, time travel shifts from being a neat trick of geometry to a battlefield of logic, where every step back raises the risk of rewriting the rules of reality itself. And yet, the universe may not leave us hanging in contradiction forever. If time travel opens paradoxes, physics itself might offer escape routes. Einstein's equations already hinted at wormholes, tunnels through space-time connecting distant points. But to hold such a tunnel open, nature demands something bizarre, negative energy, not ordinary matter, but something that pushes instead of pulls, a kind of anti-gravity fuel. We've caught glimpses of it, the Casimir effect, where empty space itself creates a measurable pressure between two metal plates, is one clue. Quantum fields ripple even in vacuum, sometimes producing effects that behave like negative energy. Could this be the universe's key to building stable gateways through time? If so, paradoxes don't vanish. They get absorbed. Wormholes might redirect contradictions, funneling them into self-consistent loops or even branching universes. Like cosmic safety valves, they'd ensure reality never snaps, no matter how wild the journey becomes. But here's the deeper question. If such structures exist, do they already lace our cosmos, invisible shortcuts just beyond our detection? Some physicists wonder if what we mistake for black holes, dark energy, or unexplained cosmic phenomena might actually be scars of ancient passages, remnants of time itself trying to fold back on itself. The science pulls us forward. The closer we look, the more the universe seems to whisper. The impossible might not be forbidden, only hidden. If wormholes are the doors of time, then causal loops are the stories that play out once you step through. Imagine this. You travel back in time, only to realize the actions you take are the very cause of the event you wanted to change. It sounds like fiction, but in physics it's a genuine possibility, the self-consistency principle. In this view, the universe doesn't allow paradoxes. Instead, it bends events so tightly that your trip through time becomes part of the story that was always destined to unfold. Think of the legendary bootstrap paradox. A scientist reads a paper on time travel, then goes back in time to hand the same paper to her younger self, who grows up, publishes it, and repeats the cycle. Who wrote it first? The answer, no one, or perhaps time itself. Black holes make this more than philosophy. Their warped space-time can, in theory, generate these closed time-like curves, paths where you loop back into your own history. If such loops exist, reality may not be a straight line at all, but a tangled weave of causes birthing effects and effects birthing causes. And here's the unsettling part. If time truly works this way, then we might already be living inside one of these loops. Perhaps history isn't a record of what happened, but a stage where the universe rehearses the same acts over and over, endlessly self-fulfilling. So, are we the authors of time, or just characters caught in a script written by causality itself? And so we arrive at the edge of the paradox, staring into a black hole not just as an abyss, but as a mirror. We've followed light as it bent, imagined wormholes stitching the universe together, wrestled with loops that erase beginnings and ends. Every path leads back to one question. What is time, really? If the Big Bang was the opening note, perhaps black holes are the silent pauses that shape the melody. If wormholes are bridges, maybe causal loops are the verses that circle back to their first line. And if time travel is possible, It might not feel like science fiction at all, but like déjà vu, the quiet suspicion that we've walked this path before and will again. The science tells us that black holes could be both prisons and portals. They threaten to erase everything, yet whisper of new beginnings. They remind us that endings aren't final, only folded, waiting to be unfolded again. And as we drift here, at the close of this journey, consider this. Maybe time is not a river flowing forward, nor a loop circling endlessly. Maybe it's a story, one the universe keeps telling itself, through stars, through black holes, through us. So the next time you look up at the night sky, remember, you're not just seeing light across space, you're seeing echoes across time. Echoes of what was, what is, and perhaps what will be again.